Have you ever wondered about the origin of the universe? How did everything we know and see around us come into existence? These are questions that have captivated the human mind for centuries, and while there are still many mysteries to unravel, scientists have proposed a theory that provides the most compelling explanation yet. This is the Big Bang Theory. This theory suggests that our universe, in all its vastness, began from an infinitesimally small point. This is no ordinary point, but a singularity, an entity of infinite density, infinite heat, and virtually no size. It's a concept that pushes the boundaries of our imagination, a state of matter so extreme that our everyday laws of physics can't fully describe it. Around 13.8 billion years ago, according to the Big Bang Theory, this singularity began to expand, not into a pre-existing space, but creating space as it grew. It was an explosion of sorts, but not an explosion of matter into space, but rather an explosion of space itself. This was not a slow, gradual process, but a rapid, explosive expansion, a moment of creation when the fabric of space and time itself came into existence. It was from this singularity, this point of infinite density and extreme heat, that all matter, all energy, and even time itself emerged. The Big Bang Theory, first proposed by Georges Lemaitre in 1927, has since been supported by a multitude of observations and experimental evidence. From the cosmic microwave background radiation to the large-scale structure of the universe, the clues all point towards this incredible origin story. So, the journey of our universe, as we understand it, began from a singularity, a point of infinite density and heat. But this is just the beginning of the story. There is much more to explore as we delve deeper into the enigma of the universe's origin. In the tiny fractions of a second following the singularity, the universe underwent a rapid expansion known as inflation. Imagine a balloon inflating from a pinpoint to a massive sphere in less time than it takes to blink. That's how swiftly our universe expanded from a state of unimaginably high density and temperature. This isn't just a wild hypothesis. It's a crucial part of the Big Bang Theory, first proposed by Georges Lemaitre in the Roaring '20s. It's a theory that's been corroborated time and again by various cosmological models, each explaining different facets of the universe's evolution, from the abundance of light elements to the large-scale structure of the cosmos. Now, you might be wondering, if the universe inflated so rapidly, wouldn't it be perfectly uniform? Well, not quite. While the universe is indeed remarkably uniform on a large scale, it's not perfectly so. There are minute fluctuations in temperature and density. These variations are what led to the formation of galaxies, stars, and ultimately us. But how do we know any of this? How can we claim to understand events that happened nearly 14 billion years ago? The answer lies in the cosmic microwave background radiation, or CMB for short. This radiation is like the universe's baby picture, an afterglow from the Big Bang that still permeates the cosmos. It provides us with a snapshot of the universe roughly 380,000 years after the Big Bang, revealing the telltale signs of those tiny fluctuations that gave rise to all the cosmic structures we see today. The CMB is not just an echo of the universe's fiery birth. It's a testament to the power of scientific inquiry. It's a cosmic whisper, telling us the story of how our universe sprang into existence from a singularity, expanded rapidly, and evolved into the vast, beautiful cosmos we are part of today. This early inflationary period gave rise to the cosmic microwave background radiation we can still detect today. So the next time you gaze up at the night sky, remember, you're not just looking at stars, you're peering back in time into the very birth of the universe. After the initial inflation, the universe continued to expand and cool, leading to the formation of atoms, stars, and galaxies. As the universe expanded, it cooled down. This cooling allowed for the formation of the first atoms, primarily hydrogen and helium. These atoms were not just randomly scattered throughout the universe, but rather they clumped together due to the forces of gravity. These clumps of atoms eventually formed the very first stars. Now, stars are not solitary objects. They form in clusters, groups of stars bound together by gravity. These clusters of stars are what we call galaxies. Within these galaxies, stars continued to form and die, a cycle that led to the creation of heavier elements, those beyond hydrogen and helium. This process, known as stellar nucleosynthesis, is responsible for the wide array of elements we see in the universe today. But how do we know all this? How do we know the universe is expanding? The answer lies in the light from distant galaxies. When we observe this light, we find that it is redshifted, This means the light is stretched to longer, redder wavelengths. This stretching of light is due to the expansion of the universe. As the universe expands, the space between galaxies also expands, and so does the light traveling through that space. This redshift is a direct observation of the universe's expansion. It's important to note that this expansion is not just something that happened in the past. The universe continues to expand even today. This ongoing expansion is a key piece of evidence supporting the Big Bang theory. So you see, from the formation of the first atoms to the creation of stars and galaxies, and the observed redshift in light from distant galaxies, we get a fascinating insight into the evolution of the universe. The Big Bang theory provides a compelling explanation for the origin and evolution of the universe, yet many mysteries remain. One of the most baffling enigmas in our cosmic puzzle is the nature of dark matter and dark energy. While we cannot see it, we know it's there because of its gravitational effects on galaxies and galaxy clusters. Dark matter, an invisible substance, makes up about 27% of the universe, while mysterious dark energy, driving the accelerated expansion of the universe, accounts for around 70%. Their existence has been confirmed, yet their essence remains elusive. Then there's the matter-antimatter asymmetry. According to the laws of physics, the Big Bang should have produced equal amounts of matter and antimatter, which should have annihilated each other completely. Yet here we are in a universe filled with matter. Why is there more matter than antimatter? This conundrum, known as the baryon asymmetry problem, is one of the greatest unsolved mysteries in physics. Our understanding of the universe's past also casts a shadow of uncertainty over its future. If the universe continues to expand due to dark energy, will it end in a big rip, tearing apart galaxies, stars, and eventually every speck of matter? Or will it expand forever, growing colder and emptier in a scenario known as the heat death? We're also left pondering over the cosmic microwave background radiation. This radiation, a relic from the early universe, is almost perfectly uniform across the sky. But why? This uniformity, or isotropy, is a conundrum known as the horizon problem. While the Big Bang theory has greatly advanced our understanding of the universe's history, it also opens the door to even more intriguing questions about the nature of reality. The universe, it seems, is far from an open book. With every answer we find, a new question arises, keeping our cosmic journey eternally fascinating. So what have we learned about the universe's origin and evolution from the Big Bang theory? Well, let's start from the beginning, quite literally. The universe was born from a singularity, an infinitely dense and hot point. This singularity began to expand in an event we call the Big Bang, occurring approximately 13.8 billion years ago. This was not an explosion in the traditional sense, but rather an inflation, a rapid expansion of space itself. As the universe expanded, it cooled, allowing particles to form. These particles would eventually coalesce to form atoms, the basic building blocks of matter. With time, these atoms gathered to form stars and galaxies, creating the cosmic panorama we see today. But the Big Bang theory doesn't just explain the formation of atoms, stars, and galaxies. It also accounts for the cosmic microwave background radiation. This radiation is the afterglow of the Big Bang, a snapshot of the universe when it was just about 400,000 years old. The discovery of this radiation in 1964 provided key evidence supporting the Big Bang theory. And let's not forget the ongoing expansion of the universe. The Big Bang theory tells us that the universe continues to expand even today, with galaxies moving away from each other. This is based on observations that galaxies farther away from Earth are moving faster, indicating that the universe is not static but dynamic and constantly changing. The Big Bang theory, while not perfect, provides us with the best framework we currently have to understand the origins and evolution of the universe. As we continue to explore and learn, who knows what new discoveries await us?